motion for freely falling bodies. We know that all freely falling bodies fall with uniform acceleration due to gravity. As a result, all the equations of motion for the uniformly accelerated bodies moving in a straight line are applicable to the freely falling bodies. So acceleration, A, produced in a body moving in a straight line is equal to acceleration due to gravity, or G. Distance traveled by a body along a straight line is equal to height above the surface of the earth, that is, vertical distance traveled by a freely falling body. So, the equations of motion for a freely falling body can be obtained from the general equations of motion by replacing acceleration A by acceleration due to gravity G and distance S by the height h. This gives us the following equations of motion for freely falling bodies. V is equal to U plus AT changes to V is equal to U plus GT. S is equal to UT plus half AT square changes to H is equal to UT plus half GT square. V square is equal to U square plus 2AS changes to V square is equal to U square plus 2GH. We will use these equations of motion for freely falling bodies to solve numerical problems. Following points must be kept in mind while solving numerical problems on freely falling bodies. 1. When a body is thrown vertically upwards, its final velocity v becomes 0. 2. When a body is dropped from a certain height, its initial velocity u is taken as 0. 3. Acceleration due to gravity g is taken as negative when a body is thrown vertically upwards. That is, g is taken as minus 9.8 meter per second square. 4. Acceleration due to gravity g is taken as positive when a body is dropped from a certain height. That is, g is taken as plus 9.8 meter per second square. 5. Time taken by a body to reach the highest point is equal to the time it takes to fall from the same height. Let me tell you a very interesting story. Newton was sitting under an apple tree and an apple fell on him. This made him think that the apple had fallen due to the downward pull of the earth on the apple. When a body is thrown up, it reaches to a certain height and then falls down. The downward pull of the earth on the body decreases its velocity until it becomes 0. And the same downward pull causes the apple to fall down from the tree. Newton thought that if Earth can attract an apple, it can also attract the moon. Is the force same in both the cases? Yes, it is the same type of force responsible in both the cases. Newton argued that at each point of its orbit, the moon falls towards the earth instead of going off in a straight rectangular path. So he thought that the moon must be attracted by the earth. But the question arises, why do we not really see the moon falling towards the earth? To understand this, we will do an activity. Take a piece of stone tied to one end of a string. Hold the other end of the string in your hand and whirl it round like as shown. You will notice that the stone moves in a circular path with certain speed, but its direction of motion changes continuously. The change in direction of motion involves change in the velocity of the stone. Thus, it is an accelerated motion. The external force F that causes this acceleration and that keeps moving the stone uniformly along the circular path is acting towards the center of the circular path. This is called as centripetal force, center-seeking force. At any instant, if we release the string, the stone flies along the tangent to the circular path at that instant. This is because the moment the string is released, centripetal force is no longer provided and the stone is free to fly off along the tangent. Based on this activity, we can conclude that the motion of the moon around the earth is due to the centripetal force provided by force of attraction of the earth on the moon. So, Newton concluded that there is a force of attraction acting between any two bodies in the universe which may be terrestrial or celestial. This phenomenon is called as gravitation. Part 2. The gravitational force of attraction between any two objects is always mutual, irrespective of the mass, size, shape, or distance between the objects. It means that if the earth attracts an apple, the apple also attracts the earth with an equal and opposite force. Now question arises, why apple falls towards the earth? And why not earth moves towards the apple? To find the answer, let us understand this fact. We know that according to the second law of motion, for a given force, acceleration is inversely proportional to the mass. This means that if the mass is less, acceleration is more. And if the mass is more, acceleration is less. Because the mass of an apple is negligibly small as compared to that of the earth, so we do not see the earth moving towards the apple. We have already studied that Newton discovered that every object attracts every other object in this universe, and the phenomenon is known as gravitation. On the basis of the factors on which this force depends, Newton formulated Universal Law of Gravitation. In this module, we will study about the Newton's Law of Gravitation. Newton's Universal Law of Gravitation. Every object in the universe attracts every other object with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. The direction of the force is along the line joining the centers of the two objects. Mathematical expression of Newton's Universal Law of Gravitation. Let A and B are two objects of masses m1 and m2 respectively, and r is the distance between their centers. If F is the gravitational force of attraction between these objects, then according to Newton's law of gravitation, the force between the two objects is directly proportional to the product of their masses. And the the force is inversely proportional to the square of the distance between their centers. Combining both the equations, F is proportional to m1 into m2 divided by r square. Replacing the sign of proportionality, F is equal to G into m1 into m2 divided by r square, where G is a constant of proportionality and is called as universal gravitational constant. From the above, we have G is equal to F into r square divided by m1 into m2. So, SI unit of G is G is equal to capital N into small m square divided by kg square. If m1 is equal to m2 is equal to 1 kg and r is equal to 1 meters, then G is equal to F into 1 square divided by 1 into 1 is equal to F. The value of G was found out by Henry Cavendish, 1731 to 1810. Numerically, G is equal to 6.67 into 10 raised to the power minus 11 Newton meter square per kilogram square. The value of G is always constant. It neither depends on the masses of the objects, nor on the distance between their centers, nor on their shapes, size, nature, or medium separating the bodies. As the value of G is very small, therefore, gravitational force between any two ordinary objects will be extremely weak. From above, we can say that universal gravitational constant G is numerically equal to the gravitational force of attraction between two bodies, each of 1 kg mass and kept at a distance of 1 meter from each other. This law is applicable to all the bodies having mass, so it is called as Newton's law of gravitation. Importance of universal law of gravitation. Newton's universal law of gravitation. Every object in the universe attracts every other object with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. The direction of the force is along the line joining the centers of the two objects. The formula reveals that when m1 and m2 are large, F is large. That is, the gravitational force of attraction between heavier bodies is larger than that between the lighter bodies. If we double the distance between two bodies, the gravitational force of attraction between them becomes 1/4. If the distance between the two bodies is halved, the gravitational force of attraction between them becomes 4 times. Importance of the universal law of gravitation explains several phenomena such as the binding of the terrestrial objects around the Earth, the holding of the atmosphere around the Earth, rainfall and snowfall on the Earth, The flow of water in the rivers. Revolution of artificial satellites around the Earth. Revolution of the planets around the Sun. The formation of tides by the rising and falling of water level in the oceans due to the gravitational force of attraction which the Sun and the Moon exert on the seawater. The predictions about solar and lunar eclipse are made on the basis of this law. Freefall, Part 1. Let us try to understand the meaning of freefall by performing this activity. Throw a stone in the air. You will find that it reaches a certain height and then starts falling down. What was the force that attracted the stone back to the surface? We have learned that the Earth attracts objects towards it. This is due to the gravitational force. Whenever objects fall towards the Earth under this force alone, we say that the objects are in free fall. Is there any change in the velocity of the falling objects? While falling, there is no change in the direction of motion of the objects. But due to the Earth's attraction, there will be a change in the magnitude of the velocity. Any change in velocity involves acceleration. Whenever an object falls towards the Earth, an acceleration is involved. This acceleration is due to the Earth's gravitational force. Therefore, this acceleration is called the acceleration due to the gravitational force of the Earth, or acceleration due to gravity. It is denoted by g. The unit of g is same as that of acceleration, that is, ms raised to the power -2. We know from the second law of motion that force is the product of mass and acceleration. Let the mass of the stone in the previous activity be m. We already know that there is an acceleration involved in falling objects due to the gravitational force and is denoted by g. Therefore, the magnitude of the gravitational force F will be equal to the product of mass and acceleration due to the gravitational force, that is, F is equal to mg. Using the equation of gravitation, we get mg is equal to g into m upon d square. Or g is equal to g into m upon d square, where m is the mass of the Earth and d is the distance between the object and the Earth. Students, here we are assuming d to be far greater than the radius of the Earth. Hence we are not considering the radius of the Earth in the calculation. Free fall, Part 2. Let the object be on or near the surface of the Earth. The distance d will be very less compared to r, the radius of the Earth. Thus we can neglect d in comparison to r. The distance d will be equal to r. The radius of the Earth. Thus, the object on or near the surface of the Earth. mg is equal to g into m upon r square. G is equal to g into m upon r square. The Earth is not a perfect sphere. As the radius of the Earth increases from the poles to the equator, the value of g becomes greater at the poles than at the equator. For most calculations, we can take g to be more or less constant on or near the Earth. But for objects far from the Earth, the acceleration due to gravitational force of Earth is given by g is equal to g into m upon d square. Mass. We have learned in the previous modules that the mass of an object is the measure of its inertia. We have also learned that greater the mass, the greater is the inertia. It remains the same whether the object is on the Earth, the Moon, or even in outer space. Thus, the mass of an object is constant and does not change from place to place. Weight. We know that the Earth attracts every object with a certain force, and this force depends on the mass m of the object and the acceleration due to gravity, or g. The weight of an object is the force with which it is attracted towards the Earth. We know that F is equal to m into a. That is, F is equal to m into g. The force of attraction of the Earth on an object is known as the weight of the object. It is denoted by W. Substituting the same in the previous equation, we have W is equal to m into g. As the weight of an object is the force with which it is attracted towards the Earth, the SI unit of weight is the same as that of force, that is, Newton. The weight is a force acting vertically downwards. It has both magnitude and direction. At any given place, the weight of an object is directly proportional to the mass m of the object. That is, W is directly proportional to m. It is due to this reason that at a given place, we can use the weight of an object as a measure of its mass. The mass of an object remains the same everywhere. That is, on the Earth and on any planet, whereas its weight depends on its location. Acceleration due to gravity of the Earth, Part 1. The Earth can be imagined to be a sphere made of a large number of concentric spherical shells with the smallest one at the center and the largest one at its surface. point outside the Earth is outside all the shells. Thus, all the shells exert a gravitational force at the point outside. Just as if their masses are concentrated at their common center. The total mass of all the shells combined is equal to just the mass of the Earth. Hence, at a point outside the Earth, the gravitational force is just as if its entire mass of the Earth is concentrated at its center. However, for a point inside the Earth, the situation is different. Due to gravity of the Earth, Part 2. Again, consider the Earth to be made up of concentric shells and a point mass m situated at a distance r from the center. The point P lies outside the sphere of radius r. For the shells of radius greater than r, the point P lies inside. Hence, they exert no gravitational force on mass m kept at P. The shells with radius less than or equal to r make up a sphere of radius r for which the point P lies on the surface. This smaller sphere therefore exerts a force on a mass m at P as if its mass mr is concentrated at the center. Thus, the force on mass m at P has a magnitude F is equal to gm into mr upon r square. We assume that the entire Earth is of uniform density and hence its mass is me is equal to 4 pi upon 3 re raised to the power 3 rho. Me upon re raised to the power 3 is equal to 4 by 3 pi rho, where me is the mass of the Earth and re is its radius and rho is the density. On the other hand, the mass of the sphere mr of radius r is equal to 4 by 3 rho pi r raised to the power 3. And hence, F is equal to gm into mr upon r square F is equal to gm into 4 pi r cube rho upon r square. F is equal to gm 4 pi by 3 rho r raised to the power 3 by r raised to the power 2. Gm me upon re raised to the power 3 into r raised to the power 3 upon r raised to the power 2. Gmme by re raised to the power 3r. If the mass m is situated on the surface of the Earth, then R is equal to Re, and the gravitational force on it is F is equal to G MEM upon Re raised to the power 2. The acceleration experienced by the mass m, which is usually denoted by the symbol g, is related to F by Newton's second law of relation. F is equal to mg. G is equal to F upon m is equal to gme upon Re raised to the power 2. Acceleration g is readily measurable. Re is a known quantity. Due to gravity above the surface of the Earth. Body above the surface of the Earth. Consider a point mass m at a height h above the surface of the Earth. Its distance from the center of the Earth is Re plus h. If Fh denoted the magnitude of the force on the point mass m, we get Fh is equal to G m E m upon Re plus h whole square. The acceleration experienced by the point mass is Gh is equal to Fh upon m is equal to Gme upon Re plus h whole square. We know that A is equal to F upon m, that is, acceleration is force upon mass. Now, for h less than Re, we get G is equal to Gme upon Re square. So, Gh is equal to Gme upon Re square into 1 plus h upon Re whole square. Is equal to G upon 1 plus h upon Re whole square is equal to G into 1 plus h upon Re raised to the power minus 2. For h upon Re less than 1, using binomial expansion, we get Gh is equal to G into 1 minus 2h upon Re. Hence, the value of G at height h above the surface of the Earth is G into 1 minus 2h upon Re. Acceleration due to gravity below the surface of the Earth. Now, consider a point mass m at a depth d below the surface of the Earth, so that its distance from the center of the Earth is Re minus d. The Earth can be thought of as being composed of a smaller sphere of radius Re minus d and a spherical shell of thickness d. The force on m due to the outer shell of thickness d is 0. Me is the mass of the Earth and Re is its radius. If Ms is the mass of the smaller sphere, ms upon me is equal to re minus d whole cube upon re cube. Taking me on the other side, ms is equal to me into re minus d whole cube upon re cube. fd is equal to gms m upon re minus d whole square. Substituting for ms from above, we get fd is equal to gme into re minus d whole cube m upon re cube into re minus d whole square. fd is equal to gme-m into re minus d upon re cube. And hence, the acceleration due to gravity at a depth d will be gd is equal to fd upon m is equal to gme into re minus d upon re cube is equal to g into re minus d upon re. Since g is equal to gme upon re square, substituting the value of g in the equation, we get gd is equal to g into 1 minus d upon re.